Good evening, ladies and gentlemen. My name is Suzanne McEndoo, and I work again in the ultra-cold quantum gases group, the physics department here in UCC. I'm going to talk a little bit about how you can do calculations with quantum whirlpools. Now, Niels Bohr, who along with Einstein was one of the founding fathers of quantum mechanics, said that if someone says he can think about quantum physics without getting giddy, it only shows that he doesn't know the first thing about it. So you can imagine, and I hope I illustrate why I get giddy working with the quantum version of this. So I'm going to let's lay out our plan for what we're going to talk about. For starters, ultra cold has been thrown around a lot, and let's just lay down what exactly is ultra cold. And I work with a specific type of matter called a Bose-Einstein condensate. And I'm going to explain what that is and talk about some of its fun properties, like its superfluid properties. And I hope to tie it all together with the application end of things and talk a little bit about how to make a quantum computer out of this whole mess. So let's just lay some groundwork, get everyone on the same page. Let's talk about temperature. Now, energy is related to temperature, right? But energy is also related to velocity. So that kind of implies that temperature is related to velocity. So if you can have a zero velocity, does there exist such a thing as a zero temperature? Yes, actually there does. There is a zero temperature. We call it absolute zero. So this kind of indicates that there could be a kind of natural temperature scale we could use. So instead of the Celsius scale, where zero is the point where water would freeze, we physicists tend to use a Kelvin scale. It's just the same, but where zero is zero velocity. You can just see, I've just put the thermometer here, 0 degrees Celsius is 273 degrees Kelvin. 0 degrees Kelvin is minus 273 degrees Celsius. So the size of the degrees is the same, we're just shifting the base point. So as I said, water will freeze at 0 degrees Celsius or 273 degrees Kelvin. So what's colder than water? Well, the air around us will turn into a liquid at about minus 200 degrees Celsius or 77 Kelvin. So let's go colder than that. Well, the vacuum of outer space actually has a temperature, and that temperature is about 3 degrees Kelvin or minus 270 degrees Celsius. And to us as human beings, that sounds absurdly, obscenely cold. But in order to talk about what I'm going to talk about now, we actually have to go colder. So what actually is the coldest thing in the universe if it's not the vacuum of outer space? Well, scientists have been able to create these clouds of atoms that are actually less than like a millionth of a degree above absolute zero Kelvin, which is unthinkably cold. And close to this point, close to the point of absolute zero where everything would stop moving, you're going to get some new and interesting physics. So let's just bring ourselves back up to room temperature for a moment. The air around us is made up of atoms and molecules, and they're all kind of whizzing around and bouncing around, and everything's going at different speeds and doing its own thing. And it's kind of like Shoppers on Patrick Street on a Saturday afternoon. However, if you go below a special temperature at these really, really cold limits I was talking about, you get a point where the atoms are no longer doing their own thing, but they're all going at the same speed, and they're kind of marching in step with each other. So they're less like shoppers, and they're actually much more like an army marching in step at the same speed. And this is something we call a Bose-Einstein condensate. And it's something that physicists get very, very excited about. It's so exciting that these three chaps, Cornell, Kesherly, and Weinman, won the Nobel Prize in 2001 just for being able to create one of these things in a lab. So why is it interesting and Nobel Prize worthy? Well, for starters, it's our quantum sandbox. It's a new place for us to play. This is an entirely new form of matter. Imagine if you lived on the surface of the sun and you discovered a fridge with ice cubes in it. And you've never seen a liquid before, really, and you've got a solid in front of you. So you'd kind of want to poke it, and you might toss it about a bit, see what happens, smash two together. And that's kind of what physicists do with these new discoveries in the lab. And it's a place where we can test out new areas of physics, like John was illustrating with the entanglement. But of course, everyone likes applications. These can be used to make really accurate clocks or other measurement devices like acceleration or gravity, and people are working on sending these up in spacecraft to space stations. But of course, they have interesting properties, and one of these properties is the superfluid property. So how do you sum up superfluid in one sentence? Well, a superfluid is a fluid that flows without friction. Now, friction you'd all be familiar with, but its job is to take energy out of the system by slowing everything down. So if you have your coffee cup in the morning, you start stirring your coffee, you put it down the counter. If you come back 10 minutes later, Because there's friction in there, everything will have slowed down and your coffee will be perfectly still, as if you'd never stirred it. However, if you had a quantum or a superfluid coffee cup, if you stirred your quantum superfluid coffee and put it down, if you come back 10 minutes later, or even 10 years later, or 100 years later, because there's no fluid to slow everything down, the liquid would still be moving, which is really quite remarkable. Now, you can just think about your coffee cup in the morning. If you stir it really, really fast, you'll get a little whirlpool or a vortex. You can do exactly the same thing with these superfluids. You can get a superfluid or a quantum vortex. And because the fluid will never stop flowing, these things are really stable, and the vortex will stay in the system for essentially forever. Now, I like vortices in quantum systems because there's something in quantum mechanics that I can show you a picture of. Now, if you think back to the whirlpool I showed you at the beginning, it was characterized by the fact there was a big hole in the ocean. And if you look at these clouds of atoms on the left, you can see that there are a different number of vortices. And you can see them in the fact that there are holes in the cloud. And you can probably see it a little bit better in the picture on the right. You've got all these holes. Now, looking at the picture on the right, you can probably see that everything is quite neat and orderly. You've got these lines, a kind of a triangular lattice of these lovely stable vortices. So, as I said, we've got this army of atoms, which is full of these really stable vortices, which are lining up in these beautiful lines. So, maybe we can do something interesting with this, right? The problem is that this whole system is rotating. So each of those red lines is actually rotating along with everything else in the cloud. So it's a little bit trickier, and this is where I come in. Basically, what I've been working on is as an theorist like John, I do simulations and calculations. And I've been working on getting the picture on the left, where you've got a bunch of vortices, and these are some simulations I've done myself. A bunch of vortices, which is moving around, to the picture on the right. And what's going on here is the fact that this cloud of atoms has been really confined in one direction, so that the vortices can't really move past each other anymore. So instead of having this triangular lattice that rotates, they actually form this really regular line, or this kind of linear crystal of vortices. So yes, maybe we can do something with this now. But before I get down to the real nitty-gritty of the applications, I'll take another quick diversion. Now, it's a fluid, it's flowing, so the flow around a vortex can go clockwise or anti-clockwise, fair enough. But because this is the giddy world of quantum mechanics, it can also flow both ways at the same time. Sounds completely insane, right? Some of you may have heard of the Schrödinger cat, right? It's a thought experiment where there's a cat in a box, and there's a 50% chance that the cat is dead. But until you actually look into the box, look in and make a measurement of whether the cat is alive or dead, you don't know. So we say the cat is both alive and dead at the same time. This is something we call a superposition. But of course, in this case, we've only got one cat. In my cloud of atom, in my vortex, I could have millions of atoms. So say I have 1 million atoms. Does that mean I've got like 500,000 going this way and then 500,000 of them going this way? That would kind of make sense, right? That's actually not what I mean at all. What I actually mean is you've got 1 million going this way and 1 million going this way, but it's the same million. So each atom is actually going both ways at the same time. It's in this superposition state. And this sounds like crazy talk, but this is the giddiness of quantum mechanics. And there is no real classical analogy. There is no real Schrödinger's cat, unfortunately. So let's get down to the nitty-gritty of the application. The information stored in the computer here is stored in binary, so zeros and ones. And physically that has to be encoded somehow. So that's current flowing will be a 1, no current flowing will be a 0. And you can draw similarities between I've got these rows of vortices. Gosh, you could say anti-clockwise is 0 or clockwise is 1. And because they're stable, your information will be stored essentially forever. But of course, because they can be clockwise and anti-clockwise at the same time, you could store a 0 and a 1 at the same time. So we call this a quantum bit or a qubit. This makes quantum computers that much more powerful than classical computers. And you can do things like if you want to search a list of numbers, instead of going through the list of numbers as you would regularly, you could have a superposition of these numbers, or look at all these numbers at the same time. And you can imagine that you'll be able to find your number much, much faster in a much more efficient way. So basically, what I'm going to keep working on here is going to keep trying to understand this linear system we've got here, and predict some of its properties, so we can kind of talk to experimentalists, and they can talk to us. and kind of work out how we can really use this to store information in the way I've just illustrated. But also, this is my idea of fun. So just to sum up, ultra-cold physics is really the coldest thing in the universe. And at these ridiculously cold temperatures, you get this army of atoms called the Bose-Einstein condensate. And this thing has superfluid properties and these vortex properties that, as I said, I find fun. And I hope I've illustrated how these things could actually have a practical application in quantum computing. So I'd like to thank you all for listening, and of course if you have any questions you can ask me now or during the refreshments, or come and talk to us. We're always happy to answer questions.